Cupipe. My name is Julia, CEO of Cupipe, overall double checker, video splicer and editor, and also co-creator of the synthetic pathway. In this video, you will meet the voice of Cupipe's CTO, Ben, who will be explaining to you the mechanism for how we synthesize our D-mannitol. You will also meet Kutjim, our COO, who's our numbers guy. So in this video, we will explain to you how we synthesize our product, what the costs look like, and why you should be interested in our product D-mannitol. D-mannitol is a very popular diuretic right now, and for good reason. D-mannitol is a sugar alcohol, which means it tastes good. Tired of pills? Sweeten your tea responsibly after consulting a doctor with our D-mannitol to decrease cranial pressure. Please enjoy the video.
In our first step, from ethanol into D-mannitol, we decided to use PCC as the reagent. So in the first step, you're going to have nucleophilic attack by the oxygen onto the chromium 4 complex that forms a chromium oxygen bond. Then in the second step, you're going to have proton transfer from the OH to the negatively charged oxygen right here onto chromium, which will form an ester linkage between chromium and oxygen. In the third step, you're going to have double bond reformation on oxygen and loss of a leaving group of chlorine that detaches from the chromium complex. In the fourth step, you'll have proton transfer onto chlorine, which will form HCl as a byproduct. This is going to cause a carbonyl formation that prompts chromium to become a leaving group. And then ultimately in the fifth step, we get the product that we were wanting is an aldehyde. You're going to have chromium 6, and then you're going to have the original PCC byproduct. So ultimately, in the formation of the aldehyde, the alcohol was oxidized into an aldehyde, and chromium 6 was reduced into chromium 4. In the next step of our synthesis, we are moving from an aldehyde into 1-methyl-pent-1-ol. So to do this, we're using a Grignard reagent followed by acid workup. So in the first step, we have the aldehyde. R prime from the Grignard will attack the carbonyl, causing the double bond on oxygen to move up into lone pairs around oxygen. In the second step, in the acid workup step, you're going to have proton transfer from this hydronium ion onto the oxygen. This is going to cause the lone pair to move back onto the newly formed H2O molecule. And in the end, we form our product, which is going to be 1-methyl-pent-1-ol. We are now moving from 1-methyl-pent-1-ol into 2-bromohexane. To do this, our reagent is going to be HBr. In the first step, you're going to have proton transfer from the H on the HBr onto the oxygen. In the second step, you have this newly formed water group. You're going to have loss of a leaving group and ultimately water formation. In the third step, you now have this carbocation intermediate that's going to have nucleophilic attack by a bromine. And then the product form is going to be 2-bromohexane. In this mechanism, we are trying to form a brominated alkane. In doing this, we are using the reagent NBS in ultraviolet light. In the first step, you have N-bromosuccinimide with UV light. This is called the initiation step, as the UV light breaks this bond and forms radicals. In the second step, these two Br radicals combined together and formed Br2. The second radical right here was already present from a second molecule of NBS that was earlier broken by UV light. In the third step, right here, Br2 is forming the radicals due to UV light. So at first they coupled, but now they're splitting. We're now moving into the propagation step of this mechanism. In the fourth step, the pooling of the electrons away from the alkane chain forms an alkane radical and HBr. In the fifth step, the Br2 radical that was formed earlier reacts with the alkane radical. This is called the termination step. In the sixth step, this cycle is going to start over again by creating more Br radicals that will couple, split, and attack the alkane chain until our product is formed, which is the brominated alkane. Shown here is succinimide that is going to be formed. So under UV light, this attacks the HBr and it's going to form two radicals. The two Br radicals are going to combine together to make Br2, which will again be split by UV light and propagate the cycle. Ultimately, this process is going to rinse and repeat until our brominated alkane is formed. In the final step of our synthesis, we're taking our brominated alkane and turning it into the alcohol sugar mannitol. In order to do this, we are using sodium hydroxide dilute at a cold temperature. This favors SN2 consortium. SN2 consortium will cause the leading group, which is bromine, to leave and nucleophilic attack to occur simultaneously. Under conditions of dilute solution of sodium hydroxide at a cold temperature, this will favor substitution and will cause the brominated alkane to form the sugar alcohol D-mannitol, which is our desired product, shown here.
Hello everyone, my name is Kutjim, the COO of Cupipe. Let me give you a cost analysis of all the reagents required for D-mannitol. Our first reagent is PCC, which costs 44 cents per gram. In low of N-butyl magnesium bromide, we can use the more available reagent, butyl magnesium chloride. It costs 26 cents per milliliter. Third is hydrogen bromide for 78 cents per gram. Next is NBS at 17 cents per gram. Our final reagent is sodium hydroxide, which costs 13 cents per milliliter. So to make 10 grams of product, it will cost $3.56. Sigma Aldrich charges $15.80 for 10 milligrams. That's $15,800 for 10 grams of product. If we sell a product in 10 milligram samples, we will make $15.08 per sample, or $15,796.44 for every 10 grams sold. Back to you, Julia.
So what should you take away from all this? Our process? Simple. Our costs? Reasonable. Our margin for profit? Huge. You won't find a sweeter diuretic. Cupipe.